Okay, yeah, thank you very much. Let's start, please, Professor Curie, for speech.
So this talk is the continuation of the previous one, but formally it is independent. And I'll start with almost the same definition, but more restrictive. So today, by descend d'enfants that we are going briefly to call it a dessin, we also mean a triple of the same kind, where x sub 0 is a finite set, and the complement from x sub 1 to x 0 is a disjoint union of intervals when, I mean, is homeomorphic to a disjoint union of intervals. So the first two terms constitute a graph. This is one of the definitions of the graph. And x2 is now, I'll draw a picture. X2 is a surface, compact, connected, and the difference between this talk and the previous one is in that it is assumed oriented, not just orientable, but oriented, which means that one of the two possible orientations is chosen. And there is the similar assumption. The graph is, well, not too poor. And, sorry, the difference between two-dimensional part and homeomorphic and one-dimensional part is the disjoint union of open cells. Well, anyone who likes it can think about multidimensional analogs. The theory of them has started in several ways, but is in no ways completed. The true goal of today's lecture is to establish the equivalence of the appropriately defined category of descents and two other categories that seem to be of different nature, and nothing like that has been formulated for higher dimensions. Okay, comes to constant. So sorry, I'm unable to recall the names now, but there were two Grothendieck students in whom I'm asking Mantrov's question now. There are two Grothendieck students with whom he worked in Montpellier on Descent d'Enfants matters, and they have published a couple of papers. So if anybody is interested, after the talk, I'll give the precise references. So now I solve the technical problem of moving this whiteboard as it was solved for the previous time. I have to find a hand, but I don't see it now. Can anybody help me? Where is the hand to move? I see it, but under the whiteboard.
Yeah, under the right underside, I can find the hand.
I'm trying to find it, but I don't. No, maybe oh yes, I had to close yes, now it works. Now it works. So now I suggest the combinatorial description similar to no, I cannot restore the drawing tools, perhaps. Cannot restore the pen. Navigation. Oh, no, something dangerous has happened. I didn't want this history, and I don't know how to remove it. Can anybody help me? So I still no, and the hand doesn't work anymore. Now it does, and now it does not. Now it works, but some extra. Do you see some extra piece in blue? Just looking for the pen. I pressed something, and I have this thing in blue.
Oh,
Good.
no, I cannot see. Sorry.
So it is just on my screen. Maybe I have enough place for that. Oh, no. Now they suggest me the history that I don't need. And the page doesn't help. Oh. I really don't know how to proceed, how to continue.
Oh, sorry.
Now they are suggesting me some changes. When I ask for the page, they suggest the same. And here perhaps what? Oh no. Oh, So I'm really confused. There is no ways to return to writing. Not that
Is there
I'm
a
aware.
toolbar? Is there a toolbar with a pen mark on it? I mean, do you see any like bars, lower right or
I have
left portion of your
three bars here, and when I press them, I see the whiteboard and some suggestions like
Oh,
save the page or
Mhm.
whatsoever.
One of the bars should have a pen icon on it, like a
Yes,
pencil.
I thought it should, and I'm looking for this pen,
Hmm.
but I don't find it at all. So,
Hmm.
it was under the yes, perhaps they suggest choose, but I cannot make a choice because it disappears immediately. No. So it suggests a bar, but suggests something like a pen, but it does not
Mhm.
work. I'm
Oh.
choos I'm choosing it. I'm choosing, but the choice disappears, and under this choice I have dots, but when I press them, I'm suggesting more advanced topic. And when I press the only remaining button, I'm suggest the some artificial intelligence tool. So
Mm.
choose. They say choose. Well, it's impossible, but
Uh,
the only thing that
can
can
you
work
try?
is perhaps I
Can you
can.
try pressing P? The
Sorry, say it again,
try
please.
pressing the keyboard P, the letter P on the keyboard,
Keyboard P. Yes, now
or
I do
Shift
it.
P.
Oh, it was simple as that. Just pressing P. Thank you very much for your
thank you very
assistance.
much.
So now it
You're
works.
welcome.
I have not the whole whiteboard available. It is spoiled by some piece, but about a two-thirds of the whiteboard seems available. So sorry for this. And now the color is still wrong. Now I'm trying P again, choosing the pen, and finally I have it. So, mm, and I'll erase this random one, P. Um, so I and tell you about the construction that is similar to the previous one, but different. So suppose we were having the sun there to the left, and we have, maybe without arguments, just the main set. That will be the set of oriented edges in the obvious sense of that graph. And I just remind you that the loops are allowed in our graph, and so they are also, the oriented loops also are parts of E. And now we are going to define the operations, three operations on this abstract set. Perhaps let's collect these operations in what Grothendieck has called the second oriented group. So generated by rho sub 0, rho sub 1, and rho sub 2, and rho with each index acts on the corresponding the piece of an oriented arrow of the corresponding dimension. So as for rho sub 0, we pay special attention to the 0 element of a directed edge, and hence this one now everything happens on the surface, so there is a global orientation, and so there is a contrary clockward direction. Well, perhaps I better draw it in a bit different way. So let it be like this. So this one is a result of rotation of that epsilon to the left, contrary clockwise. Now, as for rho 1, I won't draw it immediately here, but it is related to one-dimensional part, and therefore it just changes the direction of the arrow. And then we remind ourselves that our graph divides the surface into the pieces homeomorphic to the contractible pieces that we sometimes call countries, thinking about descent as about global geometry. So rho 2 moves, moves the edge around the country in such a way that it is stays to the left of it. Now I should not close the definition of this group, because anybody checks easily that these generators satisfy the rules. Rho sub 1 square is trivial. It is the most obvious of them, and some drawing is needed to establish another one. 0 is 1. So this is the complete presentation of it, and here is the combinatorial structure that allows to that is associated to descend in an appropriate way. So maybe I'll try to avoid the category language whenever possible. But I have not defined precisely the category of descent d'enfants. Maybe I just pronounce it briefly. But here we have a simple category. So we have a unique group somewhere. Please tell me if I continue to write here, you see it. Well, perhaps I better move. Continue to move it. So since any of the generator by the second relation, any of the generators rho sub 0 or rho sub 2 can be deleted, and we have the free product of infinite cyclic group and of the cyclic group generated by rho 1, the C2. So the whole category of descents is the category of these C sub 2 plus sets, well, finite, homogeneous is if we assume, as we did, that the surface is connected, and well, maybe mark that this C sub 2 is generated obviously by rho 1, and the only remaining condition is that rho sub 1 acts on the set without fixed points. So this is an easy way to define the category. Perhaps I should pause here a bit and ask whether there are any questions about this first language. Or maybe before that, I should stress that what we have is the construction can be formulated just in terms of finite groups, because what really works is the image of this finitely presented group in the set as a subgroup of finite groups of permutations of directed edges. And this is today I have promised 3 language vocabulary, and this is the group theoretical part. Well, perhaps I just pronounce it orally, that the class of isomorphisms of descents is defined by the conjugacy class of the image of C2 plus, or in the same way, let me move it further. In the same way, we can choose an arbitrary, directed edge, and call again, as the previous time, the Borelian subgroup just its stabilizer. So we mean that our group acts somehow on the set of directed edges. Here is its stabilizer, and then the whole set of directed edge is set theoretically by one-to-one correspondence with the classes, the orbits of B epsilon, and D, the descent is restored by its conjugacy class, by B epsilon up to, do I have it, up to the replacement of B epsilon by any conjugated class of it. So in the group theoretical language, we can work either with the subgroups of a finite group of permutations, or just our category is the category of certain subgroups of the universal groups of finite index up to conjugation. So this is the correct place to stop and to pause and ask you if any questions occur. Then, if no questions, we move to the next part of the talk, and with next P, I try to draw what is called the topological village coverings. Coverings. Now I would like to try to get rid of this part that you don't see, but I'm unable to. Sorry, and after I just put a point here, my whiteboard contents has disappeared. Well, maybe I try to no, I need the title I have already.
It's in a lower portion of the board. It's still there. If you go
Yes,
down,
but I don't see it, and just the unseen point, unseen part.
if you scroll down,
Exists. Oh, maybe we do the following. I've told you just about a third part of the program. Maybe I stop the demonstration now and start another one.
Sure.
And don't make this mistake. Now you called me. Is it okay?
Sure. Thank you very much.
But now how do I close it?
I can close. Do I close?
Please do. Please do. Close, and now I start the new one. So, but unfortunately, it still contains some piece that I don't want to. What can I do to not just to restore it, but to start a really new one? Maybe
Let
I
me
should.
try.
And now I'm pressing share and pressing the whiteboards and share it and try to share it, but nothing happens. Try again.
I opened, and you can use. Yeah, I opened new one.
Yes, here I seem to have the new one, and without that, good. So I hope it works now, and I have all the tools available. And here is the new title, then the topological Bellich covering. I'll say some words, but mostly it is going to be in the pictures. So suppose we have our surface x sub 2, and we consider a certain country there. So here is just the piece of our surface that remains after taking the complement. So maybe it is connected piece of the complement x2 divided by minus x1, and we speak about it as about a country, thinking in terms of political geography. Then we select again, I'm lost, but I'm pressing P now. Now we introduce the sorry, P. No. Yes. And now we create a point of another type and call it capital. Call it the capital. And imagine the roads that connect the capital to all the other neighboring capitals. And that means that we choose a point on every edge, a point of certain type, different type on every edge. And the last thing to do is that we connect, so we introduce the concept that does not exist in the topological, in the usual geography. The vertices become the corners of the country. And that was, there we have had the dashed lines, and here we use the pointed lines. Soon enough, I'll introduce the colors, and it will be easier to follow that. But as we see, to follow the writings, please see the upper right side.
It is just instruction to follow your
Okay,
writing.
okay, I hope they see it. And the last element of our drawing is that since it lacks just one element, since our whole surface is oriented, and now, as you see, we have created a special triangulation of it, of such a kind, of such a type that we have three kinds of vertices and three kinds of edges, and every triangle contains all the three types of vertices. And oh yes, now I have it in a tiny way, but I'll try to reproduce the final step we need. But again, the choice has avoided me. And so, as I said, since the whole surface is oriented, we can divide the triangles in, well, positively oriented and negatively oriented. And I have a certain reason, if I'm correct, to choose to color them in black and white. So it is almost unseen for me, but I'll reproduce it in a larger scale. So let it be again pentagon, larger pentagon. So I'm just reproduce it. Here are the lines of the original types. That, oh, sorry, there are some names on the whiteboard, just where I'm writing Malik Marsikar for the time being. So then there are what we can could the checkpoints on the borders. Then, well, maybe I better use the waved lines. They will be, see, they are more difficult to realize them on computers, but easily, but seen better. So there is the second type and the third type. Like this, the dash, the dotted line that constitute the triangle, the triangles of our triangulation, and our last step is color them in the chess-like matters like this. I have some reasons that I'll explain soon. Explain soon to choose which triangles are colored white and which are colored black. The thing is that we are, the title is the Belly mapping, and now we introduce the yes again everything has disappeared. I'm trying Control P, just P. It does not work, unfortunately. Something happened to the whiteboard. Yes, I hope it will work now, but I believe what I was going to draw below is now impossible. And edit the time. I should prefer to have my whiteboard fixed, because when it moves, some elements disappear.
Yeah.
And for example, now I am pressing P and nothing happens. Can you please? Yes, and now you have returned it. So. Do I find the place for the belly sphere? I can draw. Yes, maybe. Oh, yes, I even have the place to complete it. So what is called in the belly sphere? In terms of the category, it is the smallest element of our category. And now I choose the appropriate. What I'm trying to draw here, it is not really easy, is the smallest triangulation of the sphere, just in two triangles, about which we think in the following way. Well, these are going to be 0 and 1. This is going to be infinity, and then we choose the appropriate types of lines, and the dotted ones here, and then we see them on the other kind. And we choose black for the lower part of the sphere and white for the upper half. So I believe that it is not seen well, but what I'm telling you about is the black and white version of the theory. Soon I'll have time to suggest to you the colored version when everything is going to be seen better. So, can I use colors, I hope? No. In some time I'll need colors. Yes, here I see them perhaps. So what I'd like to mark now is that suppose we have identified all the pair of triangles, one of which I was tried to surround with a blue line. And when identified in an arbitrary topological way, every pair of triangle will become homeomorphic to the colored, to the black and white belly sphere. Then it defines the homotopical type of the covering of the whole, maybe I surround it symbolically by, I just remind you that we had a global surface here, and the descent and Edison defines the continuous mapping of the surface to the Belly sphere, such that it is ramified only over the 3 points. And this is what is called the topological Belly sphere. And now we turn to the other domain of mathematics, and then I'll reproduce everything in a more general setting and in color. So sorry for these not quite clear pictures. I hope they will be better in what follows. So I've promised in the abstract of today's talk the arithmetic geometry, but now we'll turn to the geometry over complex number, to algebraic geometry, after which it will turn out that all the objects will be defined over the field of algebraic numbers. But now work on C, and our sphere now, found or not, will become the projective line over complex numbers. So better call for some time, call it not Belly sphere, but a Riemann sphere. But think about it. It is sometimes difficult to draw one's spheres. So we have a certain type for our capital, our type corresponding to capitals will be in infinity, and what we'll have in the finite part of the Riemann sphere, that is just the usual complex plane, and we have it well drawn in a certain way. Here is the usual segment from 0 to 1 that was represented by the edges of initial graph. Here is the part that goes to infinity, and here we draw the triangulation, and naturally the lower half is black, and the upper hemisphere, the upper is white. So what is important now is that this object is no more just a topological sphere, but it has a complex structure. It is now a Riemann surface of genus 1. And what we have constructed, now let me use my usual notation, X in bold is x sub 2, also with a complex structure that is the only one for which, sorry, I have not introduced the standard notation, but the covering that we have constructed is, I've called it the Belly covering, but there is a traditional notation for it since our paper with Vygotsky. It is the Belly covering. Now this is the complex structure on X is the only one with respect to which beta is a holomorphic function. The Riemann surface of genus 0 has the only complex structure, and it is lifted in the only way to the structure, to complex structure on the initial surface, where it becomes bold faced. Or in a bit more traditional way, again, my point has disappeared because something changed. Choose. In other way, beta can be looked at as meromorphic function. That means that we have chosen a special point on the Riemann sphere and called it infinity, and then the divisor of beta has become, well, let me write it symbolically, the sum of the points like this. So they are zeros with multiplicities minus the sum of the capitals just turn into set of poles of the meromorphic function, and more than that, the divisor of beta minus 1 are, let me put 2 here, twice the sum of the types like this. Unfortunately, here in these two sums, I mean the sums with multiplicities, and here is the simplest sum. What I mean is that according to our construction, the multiplicities at 1 are exactly 2's, and this is the same sum of capitals. Now I'll move the whiteboard and reproduce this condition again. Cannot edit it. But in purely algebra geometric language and over an arbitrary field. So looking for my hand, don't see it. So the next title is going to be Belly pairs. Belly pairs over here arbitrary field. Let me use the traditional notation, an arbitrary field K. We assume it algebraically closed, and perhaps its characteristic, well, large enough, but maybe, let me be not quite exact here, large enough, and definitely larger than 2. And then we define exactly the same thing, but in a precise manner. So X and so some pairs are called BLE pairs. BLE, that means exactly that beta is a non-constant rational function. Below, before that, I spoke about meromorphic function on Riemann surfaces, but over complex numbers, this concept coincide. According to Riemann's existence theorem, all the Riemann surface admit the only structure of algebraic curves, and all the meromorphic functions are rational. And here we just assume that it is rational, and instead of the topological restrictions, we demand that the set of critical values of beta are precisely 0, 1, infinity. That is understood as the subset of the projective line over K, or otherwise the reformulation is that whenever the differential of beta, it is not a number, but it's becoming 0 or infinity, makes some sense. There are zeros and infinities. As soon as this happens, then beta of P should belong to the 3-element set. Again, some names here, Malik, are just when I'm trying to write. Can we try to avoid it? So this is the algebraic condition of being barely mapped. I'm not sure now whether I should rewrite it in terms of divisors. Perhaps I'll do it in the 3rd lecture. Hopefully that is going to happen in April. Then where we are going to discuss the practice of calculating Bailey pairs. The usual problem is to calculate them over complex numbers according to the data. And oh, sorry. Now I have to give a definition that corresponds to.
Excuse me, what is rho? Is rho the the differential d beta is evaluated at
the
rho
point P.
or p at the
It
point
is
p.
P. Yes, P was an arbitrary point of. I'm using different points. The bold one for algebraic surfaces and the capital for its points.
Mhm.
It is just another way to define the critical values, but more elementary definition is as follows. The rational functions on every curve define finite to one mappings of algebraic curves, well, curves to lines. And the critical values, a set of critical values is the finite set of points such that the cardinalities of pre-images is smaller than the general one, and the general one is constant, called the degree of a map. So I don't know which one is more elementary, but anyhow, we've seen it. Now, what we have drawn were the so-called clean Bialy pairs. I draw it first. Pairs. In algebraic geometry, there is a tradition to draw things like if they were defined over real numbers. It is, of course, not so, but I hope you'll follow the picture. So it is the symbolic picture of Bialy function. And what we mean, it has arbitrary ramifications over 0 over infinity and arbitrary ramifications over 0. Please, can you stop the names, icons with names stop well, floating along the whiteboard. But over 1, we have only the ramification like 2 to 1. So this is the definition of cleanness. Perhaps I better draw it. Let's remind it over C and just try to draw what happens there. So suppose this is the piece of a border. Here is the piece of a road connecting two capitals. And let's reproduce the complete picture. And here are the vertices of the original graph. And let me see the correct colors. The correct colors are like this. And beta in this notation in the appropriate, in the natural coordinates. Let's imagine that we have chosen sorry, it again, it has hidden I don't know why the whiteboard jumps.
Excuse me, Stanislav. Actually, you are clicking wrong button. If you click that
Yes.
button, then we stop the things. So please, yeah, sorry.
So I was just trying to reach some color, but I'm unable to do that. So maybe just by arrows, we can use a local coordinate such that beta would look like squaring this coordinate. This is exactly the property of BLA map that I was trying to reproduce in terms of the divisors. But I hope the clearest understanding of it is like this. So the ramification in these points of the boundary are just always two. So, and now we try to turn to the general BLA pairs, and I try to move here, and perhaps without additional words, draw the picture, the BLA for the BLA pairs. Just remove this restriction and draw it. So any branching. So I repeat it symbolically, like 0, 1, infinity. And the restriction is removed. Any branching in particular. No branching is allowed. So this is the picture corresponding to the lack of this construction. And now perhaps I better start to the right of it, introducing colors. And now I am introducing the true BLA sphere. That is a colored Riemann sphere. Now I'm using 3 colors, and here is the delicate point of it. Now I try to do it in a memorizable way. First, color the real line, and blue is going to mean cold, and red is going to mean hot, and green is in between. In between. Now the infinite. And we think about it in terms of triangles. So it is a, sorry, I have to So our lower part is still black, and upper one is white, and then we think about all the objects as about triangles with the usual rule of coloring, according to which each vertex is colored in the color of the opposite side. Therefore, the infinitum, our infinitum, is green. So this is just the definition of a Riemann sphere. So the colors are blue, green, red, and the other way to memorize it without temperature is the alphabetic order: blue, green, and red. Now suppose we had a Belly function, Belly pair over it. That means that somewhere I'd prefer to draw it over the Riemann sphere, but I have no place for it, so I'm claiming that on the original Riemann surface, here everything happens over complex numbers. We have the colored triangulation, like this triangle. This and red. It has the property that I have already pronounced in different way. Every triangle of our triangulation has the vertices of all the three colors. And the edges of all the three colors. Maybe I better draw them larger, but first I have to draw it on the surface, and I hope it is clear enough. What I really need additionally is this color, the color of the triangles itself. And the final one is blue. The rule is very simple. Any edge connects the vertices of two others. Now I have some experience to see immediately which one is white, which is black. And so we have the full triangulation like this. The colored or three-colored triangulation. I'm afraid I have no times to formalize the corresponding category. It is simpler than the black and white, and now I'm going to return to the group theoretical description of the colored triangulations. Sorry, I have lost my hand again. Oh, here is my hand, and I move it further. So maybe what I should say here is that choose Let's choose white. Triangle. And maybe I just mention that it is something like a marked point or the definition of the analog of fundamental but discrete. Will introduce the fundamental analog of the discrete group. Now I'm going to use lots of colors, or perhaps do this, the introduce the trying to. I don't need the additional instruments. I need the usual color. So introduce the set of triangles. Say T. And they constitute the disjoint union of black and white ones. And here we draw. Suppose we are inside our our distinguished triangle. And here it is. And we have three operators of moving to the neighborhood, to the neighboring triangle, just crossing the red side and crossing the blue side and crossing the crossing the greens, the greens, here is the blue one, and here the letter is wrong, and I have troubles with finding the eraser. And here is the blue one. Here is the green one. So before introducing the group theoretical machinery, let us, well, just to save time, let me sometimes not use the colors, but we have three bijections between two sets, and this is the corresponding structure. So we have the blue, green, and red bijections, or in group theoretical terms, we have another category of the sets over a certain group. So we have such a group, the free product of two element groups, and it is the group acting on the set of the whole triangle. And we select easily the so we get rid of the marked triangle by considering the classes of conjugate subgroups of finite index here. So again, we have a well-defined problem in the group theory. And again, the other version is, so what I have briefly formulated is, well, the category of conjugate classes of subgroups of this one of finite indices, or in terms of finite groups, we have the problem of the subgroup of the substitution groups. Well, that is S in original notation of Vn, but we are interested in subgroups generated by three involutions, blue, green, red. So this is a well-defined problem of group theory of substitutions. They classify, well, to have all the colored triangulations, we just take all the transitive subgroups of a group of permutations generated by elements of order 2. So now I have 6 more minutes, and relate this category to the arithmetic. So should I do to turn now? So taking into account the orientation. And just the operators of this C2, C2, C2 group is the subgroup of index 2 of words of even length. Sorry, I leave it to the participants to define the corresponding discrete fundamental group. It is very easy in terms that I have introduced, but the words of even lengths are generated by any two element. I just hope I remember correctly. maybe a small question mark here. Just take GB, R, R, RJ perhaps, with a question mark here, sorry. And we return to complex analysis. So, well, I hope to be able to say it in 3 minutes. So C contains the upper half plane. The traditional letter is tau. Again, sorry, Malik, your name is always just where I'm writing. The upper half plane, perhaps, well, let me move it to draw it more explicitly. So what we have on its border is 0 here and 2. Okay. Okay. You now this is going to be blue here and here, yes, and in as complex numbers, these are like this. The green is at the infinity, and here are the arcs. Again, one is of them is black. This one is white. So what I have drawn is the fundamental domain for the modular group, or so-called modular group gamma of 2, generated by, well, the matrices plus minus A, B, C, D are assumed to act on the upper half plane by fractional linear transformations. Sorry, may I have a couple of additional minutes just to...
No problem. Yeah.
Is it possible?
Yes, no problem.
Oh, yes, thank you. Then I'll have time. So, by definition, this gamma of 2 is the subgroup of index 6 in the whole modular group, just generated by the operators I have written above. Sorry, 2, 1. Easily memorizable, and you can check it in colors. What is the meaning of it? So this is the famous group, and what we need is its fundamental property, like the whole upper half plane. And so it has no elliptic elements. So the factorization of this group over it is the universal cover of our fundamental object. Let's denote it like triply punctured, or maybe shorter, C doubly punctured, that is C without 0 and 1, and this factorization is the universal cell covering. Now we have the picture for all the Bailey map, and let's immediately denote it like beta, infinite, and triply, also triply dotted, triply punctured. Usually we consider Bailey maps as ramified, as branched covering, but sometimes we delete the branches and it turns into the non-ramified covering. So the picture is as follows. We have our H2, well, perhaps better right, triply covered here. So this is the universal one, and use this notation. And this is the factorization over all the modular group gamma of 2, and for any subgroups of gamma of 2, again, let me remind that gamma of 2 algebraically is nothing but a free group in 2 generations. So here we have all the subgroups of finite index of the free group in 2 generators, and we have the set of factorizing the upper half planes over all such groups to get all them, to get some curves that are the natural notation for them would be triply punctured curves. And here we have all the set of punctured Bailey function. And after removing the dots, we know that the corresponding pairs are first are not only Bailey, but all the Bailey, and more than that, defined, this is the traditional notation in algebraic geometry, and though initially defined as complex algebraic curves, but there are the curves over Q bar. So sorry for technical omissions, but I believe that implicitly all the precise statement were pronounced during the talk, and thank you for your attention today.
Thank you very much. Are there any questions? Okay, thank you. And as I understand, in April 15th, Professor Gyurgi
Yes.
will give a next.
Yes, my plan for the
lecture.
next lecture is discuss the actual calculations of Bailey pairs. Now we have the graphical, we have discussed the graphical representations, but they are defined in finite amounts of informations in terms of algebraic equations with algebraic coefficients.
See. Then thank you very much. I think that's all for
Welcome.
today. Yeah, thank you very
Mhm.
much.
So, bye.
Bye bye.